Today we are looking at the p-series test, which tells us when a certain infinite sum settles down to a finite value and when it grows forever. In words, the result is this: the sum from n equals 1 to infinity of 1 divided by n to the p converges exactly when p is greater than 1, and it diverges for every other value of p. We will prove this fully first using a method called Cauchy condensation, and afterwards we will prove it again using a completely different method, comparison with an integral, so you can see two genuinely separate routes to the same answer. Cauchy condensation says this: if a sub n is a decreasing sequence of positive numbers, then the original sum of a sub n converges exactly when a new condensed sum converges, where the condensed sum is built by doubling the index, giving the sum of 2 to the n times a sub 2 to the n. Our sequence is a sub n equals 1 divided by n to the p, which is positive and decreasing, so condensation applies. The condensed term becomes 2 to the n times 1 divided by, open bracket 2 to the n, close bracket, to the p. Simplifying the bottom, 2 to the n to the p equals 2 to the power n times p, so the condensed term equals 2 to the n divided by 2 to the power n times p, which equals 2 to the power n times, open bracket, 1 minus p, close bracket. This condensed series is a genuine geometric series since each term is the previous term multiplied by a fixed ratio, and that common ratio is 2 to the power 1 minus p. A geometric series converges exactly when its ratio is between -1 and 1. Since our ratio, 2 to the power 1 minus p, is always positive, convergence needs it to be less than 1. And that happens exactly when 1 minus p is negative, in other words, exactly when p is greater than 1. Check step. By Cauchy condensation, the original series converges if and only if this geometric series converges, and we have just shown that happens if and only if p is greater than 1, matching our stated result exactly. Now let us prove the same result a second way, using integral comparison, which is genuinely different because it replaces the discrete doubling trick with a continuous area under a curve. The function 1 divided by x to the p is decreasing for positive x. So on the picture, each rectangle of height 1 over n to the p sits between two neighbouring strips of area under the curve, giving integral from n to n plus 1 of 1 over x to the p dx is less than or equal to 1 over n to the p, which is less than or equal to integral from n minus 1 to n of 1 over x to the p dx. Adding these inequalities up over all n shows that the whole series is trapped between two versions of the same improper integral. Integral from 1 to infinity of 1 over x to the p dx. So the series converges exactly when this integral converges. Evaluating that integral gives x to the power 1 minus p divided by 1 minus p, evaluated from 1 to infinity. This tends to a finite value exactly when the power 1 minus p is negative, in other words, exactly when p is greater than 1. Check step. The integral test gives the same threshold, p is greater than 1, confirming our result through this second independent method. Now the important boundary case, let p equal 1, which gives the harmonic series, the sum of 1 over n. Its individual terms shrink to 0, but the series still diverges. Here is why, using our condensation idea. When p equals 1, the condensed term 2 to the n times a sub 2 to the n equals 2 to the n divided by 2 to the n, which equals exactly 1 every single time. So the condensed series is 1 plus 1 plus 1 forever, which plainly never shrinks towards 0, and so it diverges, and therefore the harmonic series diverges too, even though its own terms are heading to 0.